Okay, it's a great pleasure to have Wu Hoang and Maria Radosh tell us about relativistic radiation reaction in higher order electrodynamics.
Yeah, thank you so much, Shadi and Michael, for inviting us. It's a great pleasure. So I'm going to talk about a paper that just recently appeared in Journal of Mathematical Physics. And we're going to talk about higher order electrodynamics. And the version of electrodynamics that we're focusing on has been introduced by at least 4 authors. So we have Bopp, Landé, we have also the work of Landé and Thomas, and last but not least, also by Boris Podolsky in the 1940s. So that's where this all came from. And essentially the idea is, how can we modify Maxwell-Lorentz electrodynamics so that we still get linear field equations and still have something maybe more complicated, but is in a certain sense better behaved. And recently, this theory has received some attention. For example, in 2014 by Zayats, and also there's this paper by Gratus-Perlik-Tupker that is a little bit related to also our work. And of course, I would like to mention that Michael and Shadi have been studying this version of electrodynamics since some time and working on the initial value problem for particles and fields. Even more recently, there has been work by Marcus Lazar and co-authors who have been looking at still a different version that involves even more higher derivatives. So they have a Lagrangian that involves even second-order derivatives of the field tensor. And we only have first derivatives in our paper. And they have been sort of thinking about the properties of that theory. So I should say that we're working in Minkowski spacetime and in Cartesian coordinates, which is important because some of the formulas that we'll show later are only valid in those Cartesian coordinates and not under, they just are not invariant under general curvilinear coordinate transformations, such as in general relativity. But this is really something where we stick to these Cartesian coordinates. So in electromagnetism, you have the field tensor, which is defined like this. And the field tensor is derived from our vector potential, as usual, where we impose some gauge, such as the Lorentz gauge. And just to recap, all of you know that Maxwell-Lorentz equations, so the ordinary vacuum Maxwell equations, are derived from a variational principle. So in the variational principle, you say that the action of the system is defined via the integral over a Lagrangian density, and it looks like this. So you have this quadratic term where you have to express your field tensor in terms of the vector potential. Then you have to vary the vector potential, and in this way you get your field equations. So this term where you have the product of electric current and vector potential, that allows you to couple your equations to some sources. So what about this higher this electrodynamics that was proposed by Bopp, Podolsky and Landé and Thomas? We have a different Lagrangian. So we start with this quadratic term in the field tensor, but then we add these terms which are quadratic in the first derivatives of my field tensor. And this is the additional contribution or correction that we have additionally. So if you look at this, for dimensional reasons, you have to introduce a constant L. And L has the dimension of length or time, depending on how you choose your units. And this is because we have a term which is quadratic in the field, but also we have derivatives. So from a dimensional point of view, you want to cancel these derivatives by multiplying with the length. And you have two derivatives, so it has to be a length squared. So this is where this characteristic length comes from. And the ordinary way to view this is to say this additional term here is something like a correction, which involves a very small length scale, so that ordinarily the other term is dominant. And only if the fields get very, if the gradients of the field get very strong, then you would expect this other term to dominate. So somehow at very small length scales in the viewpoint of physicists, this term would become dominant and somehow modify my field equations. Okay, and we're interested in how particles interact with the fields, and our particles are point particles, which we will describe by having the word lines, and all of our word lines are smooth and parameterized by their own proper time. So tau is the proper time on each of those word lines, and we have this mapping which maps tau into the position of my particle. And as usual, we have q dot, which is derivative d by d tau. That's going to be my forward velocity. And of course, we have my forward acceleration. The current is formally defined as a distribution where you take all the positions of your particle, and at each point you put a delta distribution there. So this is really something that's concentrated on the word line and will represent your current. Okay. So let me sort of jump to the solutions of the field equations, and we'll see the field equations a little bit later. But at this point, I just want to say that when you do Maxwell-Lorentz field equations, you arrive at the famous Lienert-Wiechert potentials, which represent the fields of, or the vector potential for these moving particles along those word lines. And this is the vector potential for the Maxwell-Lorentz case. And by doing something very similar, you can also solve these BLTP field equations of higher order with these higher order corrections. But the result looks different. So for the vector potential, what you get is an integral. So you get an integral where you integrate over the whole past over the infinite past of the word line up to a certain proper time, which we call tau retarded. So we call that the retarded proper time, and there's some function that you have to integrate, which involves the word line, and there's some kind of you could call it kernel, I guess, which involves the Bessel function j sub 1. Okay, and d squared is just defined like this by contraction with the metric. So everything here is sort of well defined, and the whole integral is also well defined, provided you have, suitable restrictions on the word line, which simply say that the word line moves slower than the speed of light. So here's a picture that shows you what this retarded time is supposed to be. So if you want to compute the vector potential at any point here, you go along the backwards light cone until you hit your subluminal word line. And this tells you where you have to stop your integration. So you would be integrating from the infinite past of your particle up to this point. And all of those would be contributing to the vector potential at this point. All right, so that was the case for fixed particle trajectories. So if you just prescribe those particle trajectories, then everything is clear because we can solve our field equations and we know what the associated field is supposed to be. Modulo, any solutions of the homogeneous field equations, which you can always add on top of that. But essentially, we know what the fields are that are sort of belonging to those moving particles. But now we want to make the problem more dynamical, and we would like to ask, what is the physically reasonable way to actually determine the trajectories of the point particles, provided these point particles somehow interact with each other and the field. So the physical idea is to say, well, the motion of the particles somehow radiates off fields, but maybe the fields can interact back with those particles, or you could say maybe all of the particles will interact with each other via the field. And in such a manner, there should be some kind of dynamical problem involved. And we would like to see if there's any rigorous way how we can determine these trajectories. So in order to answer such a question, we have to agree on some kind of framework. Otherwise, the problem is too arbitrary. So let me state clearly what kind of expectations we put into this problem, or we put into our paper. So the first expectation is that we have some positive bare masses of the particles, and we would like to determine the motion of the particles via an equation like this. So the left-hand side of the equation is just the force acceleration times the rest mass, and the right-hand side would be some sort of force that's acting on the ith particle. So we have a bunch of particles, and if you just pick one of them, we have an equation of motion like this. But in anticipation of the results that we have, we would like to say that this right-hand side is somehow a functional of all other world lines. So here, in principle, we could put everything. And it seems that at this stage, even if we require that the equation of motion looks like this, it's sort of way too arbitrary. So in order to get rid of this arbitrariness, we want to impose some overarching principle. And what we will show is that the BLTP field equations and the conservation of energy momentum of the whole system will actually uniquely determine what the right-hand side of this equation should be. So let me comment on the energy momentum conservation of field and particles. So this is simply based on the idea that field and particles should interchange energy and momentum with each other. And field plus particles is a closed system. So we would expect that the total energy and the total momentum are conserved. And the way we implement this principle is similar to what we do in general relativity, where we just say we have an energy momentum tensor of the total system, and we say that, you know, the divergence of this tensor is 0. But our main result will just be that energy momentum conservation plus field equation determine this type of equation of motion. Before we go into the details, let me also mention the naive approach, which unfortunately does not work. So you could just simply say, what about Lorentz forces? So the right-hand side in electrodynamics, let's just write that down as a Lorentz force, where you take the fields that you associate with all the particles together. So you sum all of the fields up. And then you contract that with the force velocity of the ith particle. That should be your Lorentz force. And there's also, of course, a charge. But unfortunately, it simply doesn't work this way, because even for this BLTP electrodynamics, if you look at the contribution from the ith particle itself, and you take the field of that ith particle, you would have to evaluate the field on the word line of the ith particle. And somehow it simply doesn't make any sense. As we shall see in a moment, the fields are well defined away from the word line, but a straightforward approach, just plugging in the position of the ith particle into your fields, just doesn't make any sense because of these singularities that you have. Of course, the history of the problem is very extensive. So one way you could think about getting rid of this problem is somehow to give the charges some kind of internal structure. So maybe they are extended objects. And that was done at the turn of the 20th century, where you assume that these charged particles have some kind of internal structure. But of course, that would be changing the basic parameters of the problem, because then you're no longer talking about point particles. Of course, Dirac had some famous insights into the point particles in Maxwell-Lorentz theory, and he tried to derive an equation of motion. But he found that due to these singularities in Maxwell-Lorentz theories, you have to, or maybe having to do something is maybe too strong. But his solution was to introduce some kind of renormalization principle. And unfortunately, it appears that that this is sort of beyond the scope of the current mathematical technology. So it's not clear in what sense we could make this totally and completely rigorous. So what we will do is we will sort of attack the problem in the framework that I've described, and we'll show that this problem, as stated, is solvable. It's quite a challenging problem. So the solution is not quite straightforward technically, but it is solvable in the context that I propose, that we propose. Okay, so here's the roadmap. We know explicitly what the retarded fields are, and I'll explain them in a moment with some technicality. But for each particle, we have the retarded fields, and we just sum all of them up in BLTP electrodynamics. Next, we just define the total energy momentum tensor. So more about this BLTP part later. But this part is just the adjusted kinetic energies of all the particles together. And we have to interpret this whole expression in the distributional sense, because as you see, for example, for this part, you already have these delta distributions appearing. Then the next step would be to show that this equation implies an explicit constraint on the particle motion, and we'll be able to figure out how explicitly this is pretty explicit. So we'll show that this, as a consequence of that, we can determine the right-hand side of our equation of motion. And once this is done, we can go ahead and look at well-posed questions, and we do that in our paper for a certain type of scattering problem. Okay, here's a quick review on the field equations, because I haven't showed you actually what the field equations are. So if you work out the usual variation of the fields for the Maxwell-Lorentz equations, you'll get this equation over here. That's sort of the inhomogeneous Maxwell part of inhomogeneous Maxwell equations. And from the fact that the fields derive from a vector potential, you of course get this integrability condition, homogeneous part of the Maxwell equations. But now you have to do the same for that modified Lagrangian. And if you do that, you arrive at this equation, which is similar to what we get from Maxwell-Lorentz, but you get this additional term with a box. And the box is indeed just the ordinary relativistic wave operator, and it's multiplied by this, this parameter L, which Podolsky and others have interpreted as a new constant of nature, which is supposed to, as I said, modify physics at small distances. So these are our field equations, and we can apply Green's functions techniques to get explicit solutions for those. And this was done classically by these classic authors. So they found these expressions already. So what we added to this is some convergence properties of these formulas. So let's first talk about the subluminal world line, and we're looking at C2 mappings that simply are defined by this property. So what we require is just the coordinate velocity. So you take the so what you have here is just the velocity of the particle with respect to those fixed Cartesian axes, and the index I is running from 1 to 3, and you just require that this is bounded away from 1 by a constant. So this is really subluminal and in a uniform sense. Okay, so this is actually the classical formula for the particle for the field of a single particle. So you see, it looks a little bit complicated, but nothing too bad here. So everything is well defined. So again, you have this integral over the infinite past, where you have to go from -infinity to this retarded time. And you have to integrate this expression, which involves some kind of space-time distance. It involves the fall velocity of the particle. It involves this scale L and just one of these Bessel functions. Of course, the charge of the particle plays a role and so on. And this vector R is the vector from the point where you want to calculate the field that points from the retarded position of the particle up to that point. So if you go back to the, I don't have a picture, I think, but if you go back to that original picture that I showed, 1 second. So if this is your position where you compute the fields, and this is the retarded position, the vector R is pointing from this to here, from here to here. But in the integral, it has a slightly different meaning. So the formula is a little bit abbreviated. So in the integral, this R means actually x minus q of tau, where you integrate over tau. So you have to go back even further up to the infinite past. But no matter, this integral is really well defined because we have nice properties for the Bessel functions, and it defines the field. And it solves the equations in a distributional sense. Okay, so the good news is that all the Cartesian components of my field tensor are bounded as you approach this subluminal world line. So that's the first question you have to ask, right? So you have this field which is well defined, which is locally C2 away from the world line. What happens when you actually approach the world line with your point X? You find that you have L infinity, which means that this is bounded. But the bad news is the limit as X approaches any specific point on the world line, that limit of the field does not exist. And this is sort of preventing the a direct definition of your Lorentz force. Because if this limit were to exist, then you might think, okay, that's what we have to put into the Lorentz force at this point. But unfortunately, it simply does not exist mathematically, and it doesn't work out this way. And also, you can also look into the paper by Gratus, Perlik, and Tucker for somewhere where they discuss this phenomenon also in more detail. But the approach that we will take is simply by using this distributional framework, we won't have to think about Lorentz forces in the first place. We just think about the distributional definitions of energy momentum, of the energy momentum tensor, and that totally makes sense. It's completely rigorous, and from there we'll get our equations of motion.
Okay, this is my cue to take over and to show you how we start out with the energy conservation. So that's our fundamental principle. We take the total energy momentum tensor consisting of the kinetic parts plus the field part and the energy momentum conservation tells us that the divergence is 0. But how do we interpret this divergence? Since those are, at least this one is already pretty clearly a distribution, we have to interpret this in the distributional sense. And the distributions will be acting on smooth functions with compact support. So the field energy momentum tensor has a very complicated structure, as shown here. The first line is the part that's already present in the Maxwell-Lorentz case, and the other parts come from the corrections due to the BLTP theory. And what you can see here is that this field, the tensor is quadratic in the field. So every summand here has 2 f's. This is why we wrote here f, comma f to highlight the bilinear structure. We could write it down as a bilinear form and symmetrize it. And this is something that we do when we do this theory for multiple particles. But let's first stick with just the one particle case and with this energy momentum tensor for the field. So when you take this field and compute the divergence directly, like really computing it, you find out that you get this minus field times the current. So this is the same formula that you get when you do the same for the Maxwell-Lorentz case. So you see here that the BLTP theory is a proper electrodynamics in the sense that it reproduces the physical laws that it should reproduce as a electrodynamical theory.
That's only for smooth fields.
For smooth fields, yeah. And now to our main theorem, if we have a couple of particles with their world lines, we can first state that the total field energy momentum tensor is a distribution. And the following implication, if we have energy momentum conservation, then we have necessarily that these energy equations of motions hold with a Lorentz-like force that consists of the sum of all the Lorentz forces exerted by all other particles, plus a contribution that has this form with an integral that extends over the infinite past till the point t where we are at, over this Bessel function kernel again. That looks very much alike the field, the representation for the field. So, and here is the velocity. So it really looks like a Lorentz force here. So looking a little bit more closely, the field tensor is a L1 log function that acts as a distribution by integrating it against the test function. And the distributional divergence of this tensor is given by this formula. So it acts on a test function as integrating this Lorentz force against a test function along a world line. So we will show this too. And in order to show this too, it turns out that it is advantageous to have a certain set of coordinates and not work with Cartesian coordinates, but with something that we call retarded light cone coordinates. So along the world line, we are introducing a local coordinate system by an orthogonal tetrad. So the first vector goes in velocity direction, and the other three we don't matter that much as long as they are all orthogonal on each other and move along with a world line in a smooth way. And for any spacetime event, we introduce the coordinates tau, r, theta, and phi that map into the Minkowski coordinates in the following way here with this formula down here. So I can show it maybe at this point. So if here is a point x, its coordinates tau, r, and so on come from going back to the retarded time on the world line. This will be the tau of this point x here, is the tau that Q has at this point. And then we go along the light cone, the proper distance that we want to. So from the point Q alpha of tau, we go along the light cone the distance r and arrive at the point x. And n is a normal vector in spatial direction, and u plus n then makes it a light-like vector. So those coordinates are really convenient because they make the formulas look much easier than they would have in Minkowski coordinates. So this is also a good time to introduce the world tube. So around a world line, we can define a world tube that's like a cylinder and being equipped with these coordinates, with the world tube coordinates. So this is the formal definition. It's exactly the same cylinder you would get with Cartesian coordinates, but now the r goes in the direction of the light cone and not just parallel to the space. So in order to do proper integration on the boundary, we also need the associated surface element, which has a pretty easy form here with the polar coordinates, an epsilon square, and the outer pointing unit normal vector given by this formula. And so we can calculate the distributional divergence of t acting on a function phi by just cutting out the world tube around the world line and applying Gauss theorem. So the integral then reduces to the integral over the boundary of the world tube, and then we take epsilon to 0 to close it again. So then to compute this, we just have to plug in what we have found out here for the d sigma d, that's this here, and the proper integrations. Here's the epsilon coming from here, epsilon square. And so the only thing we have to compute is the contraction of the energy momentum tensor with the outer unit normal on the world tube. The energy momentum tensor consists of two parts, where the second part is the part from the Maxwell-Lorentz theory. And this part does not contribute as epsilon goes to 0 because it's already from the order, I think, epsilon. And so for epsilon to 0, it will just give 0. So we have to concentrate on the part that is really newly introduced by the BLTP theory. And this part, to compute this part, we need to see some asymptotics of some key elements on the boundary of the world tube, which is this. On the boundary of the world tube, the outer unit normal is basically the same as the spatial unit normal. And then some parts here that appear in the energy momentum tensor have different severenesses of epsilon. So the worst one is this middle one, where we have that the anticommutator of the derivative and the Lienert-Wiechert potential contracted with the outer unit normal vector gives you an epsilon to the -2, which seems to be a dangerous term when you want to let epsilon go to 0. But the good thing is, have a look up here. We still have an epsilon squared from the integration, from the determinant of the integration. So this will kill this epsilon squared, and everything else which is of lower order will go to 0. And the only terms that will stay are terms of this sort. So if you have these asymptotics, you can plug them into the contraction of the relevant part of the energy momentum tensor with the unit autonormal. And at first it looks pretty nasty. So this is what you would get. But miraculously, after some persistent calculation and simplification, it will just give you the Lorentz force here and an epsilon to the -2 up here, which will be cancelled as we've seen before. And so this is the only thing that will survive the epsilon to 0 procedure. And yeah, that's basically how the proof goes, modulo how you get from here to here and how you get the asymptotics, which is quite technical. And yeah, we still have time left. So I would say the next thing that we're gonna touch upon is the variational principle. So we are going to introduce a variation principle that will give us the same equations of motions that we got from the energy momentum conservation. So here it's difficult to make a global variational principle, but we can do it on a local scale. So for any compact region, we can write down this following action functional that has the following parts. It has the BLTP Lagrangian corresponding to the field. Then it has this Lagrangian that gives you the contributions from the currents. Or in this case, we just look at the single world line. So that's a current. And then you can have some external potentials that you also take in, and the kinetic energy part. Yeah, and for the variation principle, we have to make sure what we're gonna do the variations of. So we are going to make variations of the world line. So we suppose that the original world line is embedded in a family of world lines with a parameter sigma. Sigma equals 0 being the original world line. And then we look at how the action functional is changing when we change the world lines. So the main theorem about that is that if the derivative of the functional with respect to sigma is given by some BLTP boundary term that does not depend on sigma and is only given by the functionals on the boundary, then necessarily the original world line has to satisfy this following equation of motion with the same here external, and here, of course, we don't have the other particles here because we are here in the single particle case. But you can imagine that if you have other particles, then they would go into this external field here. So the main work of doing—
Maria, question, what is the interpretation of the curly F here? Is that the self-force?
Yeah, that's the same. Yeah, exactly. The curly F is exactly the same curly F we had up here. Where is it? Yeah, it's here. Mm-hmm. It's the force that is being exerted by the particle itself via retardation on its own fields. And
right.
And we just put here an external force in view of having all the other particles.
So the purpose of the variational principle is to derive that formula?
Yes. And how you do it is a similar way, like with the original variational principle. So you do the variation and you show that this variation is, where is it? So here the d sigma I is constant. So it's the same thing for every sigma. And so it can only be true when you look into the integrals if this equation holds.
Okay, so now I'm just trying to understand. So, but you had this equation of motion before. So was that, were you just assuming before that that's the equation of motion, or?
No.
In two ways.
It's just two ways. So one way to get this equation of motion is to assume energy momentum conservation.
Okay, that was the other assumption. Okay,
yeah.
Right. So the other assumption was that the full energy tensor is divergence free.
Yeah, that was one way to derive it. And then once it's done, you could also say there's other ways to derive the same equation of motion, which makes it really interesting that you have different ways, different principles to derive the same equation of motion, which is quite nice. Yeah, it makes it seem more deep. Like
but here you also have an assumption, right? So this is this is the other assumption. So you're going to tell us what that is?
Yeah, I can show. Can I show the? So you're interested how this BLTP boundary theorem works?
Well, I just wanted to know if you're going to tell us what it is, because you're not. Yeah, I mean, you're just saying that if this is an assumption, if this is true, then we have this equation of motion.
Yeah, that's right. So if we have the following, if you know, the very classical variation principle is if the variation of the action functional is 0, then you have the equation of motion.
Well, with respect to compactly supported variations, but presumably your variations are not compactly supported here?
They are. So our variation, they all take place inside the omega.
But only for the word lines are the word lines vary. The variation of the word lines are compactly supported, but the corresponding fields are not. What we're doing is we're varying the word lines, and the fields are tied to the word lines, so that on the boundary of the omega, they do change. So it's not like in the usual derivation in theoretical physics textbooks where you just say you vary the vector potential and the variation is 0 on the boundary of your domain. And in order to get the correct equation of motion, you have to subtract a certain boundary term.
Yeah, but this boundary term that comes only from the change of the potential on the boundary.
Yeah, it looks very complicated, but you have to do that. Otherwise, you won't, you won't arrive at what you want.
Yeah, and it's not actually that unusual because in general relativity, you have a similar principle that you also use like a common boundary term that only depends on the potential there while doing variation inside the domain omega. So it's doing this local kind of variation principle. It's sort of to be expected that you have a boundary term, and that is not really 0 here.
Very interesting.
I don't know if there's anything to show inside the boundary term itself. It's kind of messy.
Yeah,
and
we can show it later in the paper. It's very messy.
And we don't really have insight what the parts mean in these boundary terms. For us, it's just a boundary term that's always present when you do a variation inside. And as long as the variation gives you this boundary term independent of at sigma, this special boundary term, you get then the
Yes. No, this is very interesting. Actually, we can talk about it more. Why don't you go on, and then after you're done, we could discuss more.
Yeah. So this as I said, the main work is to justify the exchange of the derivative of sigma and the integration over this integration over this omega, because all these terms here are slightly singular, and so you have again to cut out the world line, the world tubes around the world lines, and do some Gauss tricks, and then interchange differentiation and integration, and then close it again. And so this actually, after you've done it, you see that you have to postulate this in order to make this derivative equal the boundary term that we are expecting. So, and yeah, that was the part for the variational principle. And we just wanted to show off a little bit about the scattering part. A scattering part we did with the classical fields E and B that are given by these formulas. If you want to have the electrical and the magnetic fields, those formulas are nicer to work with in the scattering setting. And you have in this, you have the equation of motion, like the rest mass times the relativistic velocity is equal the Lorentz forces plus some external force. And we want this external force to have compact support, to be just a scattering obstacle. And this is the main theorem. So we have a scattering obstacle given by an external force with compact support. And then we can show the equation of motion has a global in time solution. And as the scattering conditions we impose is that at infinite past, the particle was at rest and situated at the origin. And this, this solution is unique. And this actually, due to some magic of the Bessel functions, we can apply Banach's fixed point theorem to first show a local continuation. And then you can show that after you continue a little bit, the E and the B field, magnetic and electric field, are still finite. And as long as they are finite, you can always go some more and some more. And this gives you the global part. So I think, yeah, this was all that we wanted to tell about it, and we are looking forward to the discussion.